Hello there, beautiful human. It's your boy Chad. The only channel in the known universe where the science is impeccable, the vibes are immaculate, and the host is, let's be honest, built different. Now, wherever you're watching from tonight, whether you're tucked into bed in Tokyo, sprawled across your couch in Toronto, half asleep in Melbourne, or floating in a hammock between two trees in Timbuktu, I want you to know that you are exactly where you need to be. Are you comfortable? Good. Because tonight, I'm taking you somewhere that makes the farthest edges of the observable universe look like a short commute to the corner shop. Tonight, we are talking about gravitational waves, the ripples that move through space and time itself, born from the most catastrophic collisions the universe has ever witnessed, traveling at the speed of light for billions of years, and arriving here, at this pale blue dot, as a tremor so unimaginably small that it makes an atom look like a continent. And yet, and this is the part that should absolutely rewire your brain, we detected them. Humanity figured out how to hear the universe whisper. So settle in, let your muscles relax, let your breathing slow just a little. And if it feels right, drop a like and subscribe. It really helps me give you more certified Chad tier cosmic content. Now let's begin. Have you ever stood in a very quiet room, not just quiet, but truly deeply silent, and become aware of things you'd normally tune out completely? The distant hum of a refrigerator, the subtle creak of a wall settling, the low rumble of a truck on a street 2 blocks away, traveling through the floor and into your feet. In those moments of stillness, you start to realize how much information is moving through the world at all times, carried by vibration, even when you can't see a thing. That sensation is a useful starting point for understanding what gravitational waves are, and why detecting them is one of the most astonishing things our species has ever accomplished. For almost the entirety of human history, we have understood the universe through light. Every telescope ever built, whether it captures visible light, radio waves, X-rays, infrared radiation, or ultraviolet light, is fundamentally a device for collecting and interpreting electromagnetic radiation. Light has been our only real messenger from the cosmos, and it has been extraordinary. Through light, we have mapped galaxies billions of light years away, dated the age of stars, watched matter spiraling into black holes, traced the large-scale structure of the universe, and even detected the faint afterglow of the Big Bang itself. But light has limits. It can be blocked by dust. It can be absorbed by gas. It scatters and bends, and crucially, the very earliest moments of the universe, the first 380,000 years after the Big Bang, are forever hidden from us behind a wall of hot, dense plasma that light simply could not penetrate. For those first hundreds of thousands of years, the universe was opaque. The light from that era, when it was finally released, is all we can ever hope to see. The universe before that moment is, from the perspective of electromagnetic astronomy, invisible. Gravitational waves are fundamentally different. They are not light. They are not particles. They are not any kind of electromagnetic radiation at all. They are distortions in the very geometry of space-time, ripples that pass through matter almost entirely without interacting with it. A gravitational wave traveling through a planet doesn't bounce off it, doesn't slow down, doesn't get absorbed. It simply passes through, carrying its information perfectly intact across any distance, largely unimpeded by anything the universe can put in its way. This means that gravitational waves represent a completely new sense for exploring the cosmos. If light gives us vision, a way of seeing distant events, then gravitational waves give us something closer to hearing, or perhaps touch, a way of feeling the universe's most violent events through the medium of space-time itself, even when they occur behind walls of gas and dust that no telescope could ever penetrate. To understand what gravitational waves are and where they come from, we need to begin with the theory that predicted them over a century before we were capable of detecting them. We need to begin with Albert Einstein and with his general theory of relativity. In November 1915, Einstein published what is, by virtually universal agreement among physicists, the greatest single intellectual achievement in the history of science. The general theory of relativity replaced Newton's picture of gravity, in which massive objects reached across empty, fixed, absolute space to pull on one another, with something profoundly different and profoundly stranger. In Einstein's picture, space and time are not separate, independent entities. They are woven together into a single 4-dimensional fabric called spacetime, and massive objects do not pull on each other directly. Instead, they curve the space-time around themselves, and other objects move along those curves following the contour of the fabric as though rolling across a landscape shaped by the distribution of mass within it. You've heard the classic analogy before, and it's worth returning to. Imagine a heavy ball placed at the center of a stretched rubber sheet. The ball sinks down, creating a depression in the sheet. A smaller ball rolled nearby doesn't move in a straight line. It curves toward the heavy ball, following the curved surface of the sheet. In Newton's picture, the heavy ball is sending out a force that grabs the smaller ball. In Einstein's picture, the heavy ball has changed the shape of space, and the smaller ball is simply following that shape. Gravity is not a force transmitted across space. It is the shape of space-time itself. Now here is the key insight that leads us directly to gravitational waves. If space-time is a fabric that can be curved and distorted by mass, then what happens when massive objects move? What happens when they accelerate? When two massive objects orbit each other, spiraling inward, or collide catastrophically, what does space-time do? Einstein worked this out in 1916, just 1 year after publishing General Relativity. He showed, through a careful mathematical analysis, that accelerating masses, particularly those moving in asymmetrical ways, like two objects orbiting each other, should produce ripples in space-time. These ripples would spread outward from the source at the speed of light, carrying energy away from the system, squeezing and stretching the fabric of space as they propagated. He called these ripples gravitational waves. And then almost immediately, he began to doubt that they were real. The mathematics said they existed, but Einstein worried that what the equations were describing might be in a sense an illusion, an artifact of the coordinate system he was using to describe space-time, rather than a genuine physically meaningful phenomenon. He oscillated on this question for decades. In 1936, he co-wrote a paper with Nathan Rosen arguing that gravitational waves did not actually exist. The paper was submitted to the Physical Review Journal, where a reviewer identified a mathematical error. Einstein, somewhat irritably, withdrew the paper without accepting the referee's critique, and then, after working through the problem further, reversed his conclusion and republished in a different journal with the opposite result. Gravitational waves, he concluded again, were real. This is not a failure of Einstein's intellect. It is a demonstration of how extraordinarily difficult general relativity is, even for its creator. The equations are among the most complex in all of physics, elegant in form, but ferociously demanding to solve and interpret. That Einstein got confused about their implications is a measure of the theory's depth, not his limitations. By the middle of the 20th century, the physics community had largely converged on the view that gravitational waves were genuine physical phenomena. The next question, the one that would define the following half-century of effort, was whether they could ever actually be measured. Let's think carefully about what a gravitational wave actually does as it passes through a region of space. Imagine a perfectly circular ring of small particles, all floating freely in space, with no forces acting on them except gravity. Now imagine a gravitational wave passes through that ring, traveling perpendicular to the plane of the ring, coming, say, straight down from above. As the wave passes, it would alternately stretch the ring into an ellipse in one direction, say left and right, and then squeeze it into an ellipse in the other direction, up and down, and then back to a circle, and then to the first ellipse again, and so on, oscillating back and forth as the wave passes through. The wave is not pushing or pulling the particles in any conventional sense. It is changing the geometry of the space that the particles occupy. The distances between them are changing, not because the particles are moving through space, but because the fabric of space itself is being stretched and compressed by the passage of the wave. Now here is the number that tends to stop people in their tracks. The gravitational wave from the very first detection, produced by two black holes colliding over 1 billion light-years away, stretched and compressed the LIGO detectors by approximately 1,000th the diameter of a proton. A proton is already roughly 1 femtometer in diameter. That is 1/1,000,000th of a billionth of a meter. It takes about 100,000 protons lined side by side to equal the width of a single hydrogen atom. And the change in length we are talking about is 1,000th of even that. This is a number so small that it exists at the very boundary of physical meaningfulness, the scale at which quantum uncertainty begins to complicate the notion of a defined position at all. And yet, we measured it. How? The answer lies in a technique called laser interferometry. If you've heard of interferometers before and glazed over, give this a chance. The principle is genuinely beautiful. An interferometer works by taking a single beam of laser light and splitting it into two beams using a half-silvered mirror called a beam splitter. The two beams travel along two perpendicular paths. The two arms of the interferometer bounce off mirrors at the far ends, and return to the beam splitter, where they are recombined. When the two beams recombine, they interfere with each other. Light, like all waves, can add together constructively, producing a brighter spot, or cancel each other out, destructively, producing darkness. The precise pattern of light and dark produced when the beams recombine depends on the difference in the lengths of the two arms. If both arms are exactly the same length, the beams travel exactly the same distance, arrive exactly in phase, and produce a constant, predictable interference pattern. But if a gravitational wave passes through and stretches one arm while squeezing the other, even by an amount far smaller than a single atom, the path lengths become slightly different. The beams return slightly out of phase. The interference pattern shifts, and that shift can be measured. The LIGO detectors, the Laser Interferometer Gravitational Wave Observatory, are built on this principle, scaled up to an extraordinary degree of precision. The arms are 4 kilometers long. The laser beam does not simply travel down each arm once and return. It bounces back and forth between the mirrors hundreds of times, so the effective path length is over 1,000 kilometers. The mirrors are among the most perfectly polished objects ever created. They are suspended by fine glass fibers to isolate them from ground vibrations. The entire beam path operates inside an ultra-high vacuum, one of the best vacuums ever created on Earth, to eliminate any disturbance from stray air molecules. Even the quantum nature of light itself introduces an irreducible noise floor that the engineers have had to find clever ways to mitigate. And even with all of this, the challenge is immense. The Earth vibrates constantly. Ocean waves crashing on coastlines thousands of kilometers away send seismic tremors through the ground. Wind loading on the buildings creates tiny vibrations. Traffic on roads miles away perturbs the ground. Even the thermal motion of atoms in the mirrors warming slightly and flexing by unimaginably small amounts, creates noise that must be tracked and understood. The teams at LIGO spent decades characterizing and reducing all of these noise sources, developing an almost encyclopedic knowledge of every way the real world interferes with a perfect measurement. This was, in many respects, as great an achievement as the detection itself, because to measure something 1,000 times smaller than a proton, you first need to understand everything else that might move your mirrors by 1,000 times more than that, and eliminate it, or subtract it, or account for it precisely enough that the gravitational wave signal can be pulled out of the noise. The detection of gravitational waves was not a sudden moment of inspiration. It was the outcome of one of the longest sustained scientific endeavors in history. A multi-decade project involving thousands of people, multiple generations of physicists, and a level of institutional commitment that is genuinely rare in science. The modern era of gravitational wave detection begins, in a meaningful sense, with Joseph Weber. Weber was a physicist at the University of Maryland, who in the late 1950s and 1960s became obsessed with the idea that gravitational waves could be detected. He built what became known as Weber bars, large cylinders of aluminum, roughly 2 meters long, suspended and isolated from external vibration, and instrumented with piezoelectric sensors that would detect the tiny resonance a passing gravitational wave might induce in the bar. In 1969, Weber announced that he had detected gravitational waves. The physics community was electrified. Here was a claim, backed by real data, that one of the most exotic predictions of general relativity had been observed directly. The excitement was followed, over the next few years, by deepening skepticism. Multiple groups around the world built their own Weber bars and tried to replicate his results. None of them could. More troubling, analysis of the signals Weber claimed to have detected suggested they were far too strong to be consistent with other observations. If real, they would imply that the galaxy was losing energy to gravitational waves at a rate that would cause it to evaporate on a timescale shorter than its observed age. The consensus today is that Weber's signals were not genuine gravitational wave detections. They were noise fluctuations that he misinterpreted. His statistical analysis had flaws that were not recognized at the time. But Weber's legacy is significant. He made gravitational wave detection a serious pursuit. He showed that someone was willing to build hardware, collect data, and stake their reputation on the attempt. And his work inspired a generation of physicists who would eventually succeed where he had not. Among those inspired was Rainer Weiss, a physicist at MIT. Weiss was an experimentalist of the highest order, someone who approached problems by first understanding, in minute detail, every physical process that could interfere with a measurement. While teaching a course at MIT in the early 1970s, Weiss worked through a careful, systematic analysis of laser interferometry as a method for detecting gravitational waves. He identified every major noise source, estimated its magnitude, and figured out, at least in principle, how each one could be addressed. He published this analysis in 1972 in an MIT technical report that essentially laid out the blueprint for LIGO. It was one of those rare papers that defines a research program for decades. At Caltech, the theorist Kip Thorne was developing a complementary perspective. Thorne had devoted much of his intellectual life to understanding the most extreme predictions of general relativity, black holes, neutron stars, and the gravitational waves that interactions between them would produce. He built up, over many years, a sophisticated understanding of what kinds of events would produce detectable signals, how strong those signals would be, and at what frequencies the waves would oscillate. This theoretical work was essential for knowing what to look for. The third key figure in LIGO's founding was Ronald Drever, a Scottish physicist who had developed his own independent approach to interferometric detection at the University of Glasgow before coming to Caltech. Drever had a remarkable talent for hands-on experimental physics, an intuitive understanding of how to make instruments work that complemented Weiss's more analytical approach. He brought new ideas about how to stabilize laser frequencies, how to isolate mirrors, and how to squeeze every possible bit of performance out of an interferometer. In 1984, Weiss, Thorne, and Drever co-founded LIGO as a joint project between MIT and Caltech. The funding came from the National Science Foundation, and building the actual detectors would eventually require over $300 million. The road from founding to first detection was not smooth. In the early 1990s, the project faced a serious funding crisis. Congressional skeptics questioned whether it made sense to spend hundreds of millions of dollars on an instrument that, by the honest admission of its proponents, might not detect anything for 10 or 20 years. The case for LIGO was a case for long-term investment in fundamental science, the kind of argument that is always difficult in a political environment focused on near-term results. Barry Barish, a particle physicist with extensive experience managing large scientific collaborations, was brought in to lead LIGO. He transformed the project from an academic collaboration among a small number of groups into a major scientific organization with the management structure, governance, and technical discipline needed to actually build and operate two large-scale interferometers. Barish also built the international network of scientific collaborators, the LIGO Scientific Collaboration, that would eventually involve thousands of researchers worldwide. His leadership is widely credited with the organizational transformation that made detection possible. The first generation of LIGO detectors, Initial LIGO, began science operations in 2002. They ran on and off for several years, collecting data and searching for signals. They found none. This was, to be clear, expected. The instruments were sensitive enough to establish the technology and demonstrate that large-scale interferometry could work, but not sensitive enough to detect gravitational waves from the kinds of astrophysical events that occurred with any regularity within the accessible range. Between 2010 and 2015, the detectors were shut down and rebuilt, essentially from the ground up. Every major system was improved. New mirror coatings reduced thermal noise. New suspension systems, using multiple layers of pendulums, reduced the coupling of ground vibrations to the mirrors. The laser power was increased. Sophisticated quantum optics techniques were implemented to reduce the noise floor imposed by the quantum nature of light itself. The result, advanced LIGO, was a detector roughly 10 times more sensitive than its predecessor, capable of detecting events in a volume of space roughly 1,000 times larger. It was this upgraded instrument that on September 14, 2015, detected the first gravitational wave in history. The signal arrived at the Livingston, Louisiana detector at 5:51 in the morning, Eastern Time. It was a Monday, September 14, 2015. Most of the LIGO team was not yet at their computers. The event is now designated GW150 for gravitational wave, followed by the date in year, month, day format. It is a name that will, I think, be remembered as long as the history of science is remembered. The two LIGO detectors, one in Livingston, Louisiana, set among pine forests in the American South, and one in Hanford, Washington, in the high desert of the Pacific Northwest, are separated by about 3,000 kilometers. A genuine gravitational wave, traveling at the speed of light and arriving from some direction in the sky, would reach the two detectors at slightly different times, the maximum delay being about 10 milliseconds depending on where the wave is coming from. The signal arrived at Livingston first, and at Hanford 7 milliseconds later, and the waveform, the precise shape of the signal, matched at both detectors. That match is crucial. Random noise events at one detector are not correlated with random noise events at the other. The chance of a spurious noise event at Livingston producing a signal that accidentally matches a noise event at Hanford 7 milliseconds later is extraordinarily small. When scientists see the same signal at both detectors, separated by the right time delay and with the right waveform, they can be highly confident they are seeing a real gravitational wave. When they analyzed the signal, they found that it matched almost perfectly the predictions of general relativity for a very specific type of event. Two black holes in a close orbit, spiraling inward, losing energy to gravitational waves, drawing closer and faster until they merged into a single larger black hole. The wave had the characteristic shape that physicists call a chirp. As the two black holes spiraled closer together, they accelerated, like a figure skater pulling their arms inward to spin faster. This acceleration produced gravitational waves of increasing frequency and increasing amplitude. The frequency swept upward from about 35 Hz, a low, deep rumble, well within the range of human hearing, to about 150 Hz, over the course of roughly 2 seconds. And then, as the two black holes merged into one, the signal reached its peak and fell away almost instantly. The black holes involved were enormous. One was approximately 36 times the mass of our Sun. The other was approximately 29 solar masses. When they merged, they formed a single black hole of about 62 solar masses. If you do the arithmetic, you'll notice that 36 plus 29 equals 65, not 62. 3 solar masses are missing. 3 times the mass of our entire Sun was radiated away as gravitational waves in a fraction of a second. For that brief, violent moment, the power output of those merging black holes exceeded the combined luminosity of every star in the observable universe by a factor of roughly 50. Not the light output. Black holes don't shine in any conventional sense. The gravitational wave power output. In a fraction of a second, more energy was released as ripples in spacetime than all the billions of galaxies we can see produce as starlight in the same interval. And that colossal release of energy, after traveling for over 1 billion years across the expanding universe, arrived at Earth as a distortion in spacetime so small that it strained the very limits of what is physically measurable. The first person to see the signal, a postdoctoral researcher named Marco Drago, working in Germany as part of the LIGO scientific collaboration, initially wondered if it was a test signal. LIGO has a deliberate practice of injecting fake signals into the data stream to make sure the analysis pipelines are functioning correctly. These hardware injections, as they are called, are authorized by a small number of people who keep the details secret until after the rest of the collaboration has analyzed the signal. It took several frantic hours to confirm that no such injection had been authorized. The signal was real. The collaboration spent nearly 5 months checking and rechecking every aspect of the data before announcing the result. On February 11, 2016, press conferences were held simultaneously in Washington, D.C., and at LIGO facilities around the world. Kip Thorne, who had devoted more than 40 years of his professional life to making this moment possible, was visibly emotional. Rainer Weiss, who had written the blueprint for the detector in 1972, acknowledged the journey with characteristic understatement. In 2017, the Nobel Prize in Physics was awarded to Weiss, Thorne, and Barish for the detection. Ronald Drever, one of the co-founders and a crucial contributor to the experimental program, had developed dementia in his later years and passed away in March 2017. Just months before the Nobel announcement. The prize cannot be awarded posthumously, but within the gravitational wave community, his contributions are remembered clearly. GW150-14 was not a singular event, it was the opening of a door. Since September 2015, the LIGO detectors joined in August 2017 by a third detector called Virgo, built in Italy near the city of Pisa by a European collaboration, have detected dozens of gravitational wave events, and the catalogue continues to grow with each new observing run. Not all of these events are the same. The universe produces gravitational waves in a variety of ways, and each variety tells a different story about the cosmos. Binary black hole mergers, 2 black holes spiraling into each other and merging, are the most commonly detected type. Black holes can be very massive, and the more massive the objects, the stronger the gravitational waves. The events detected by LIGO and Virgo span a wide range of masses. Some involve black holes of only a few solar masses. Others involve black holes of tens or even hundreds of solar masses. Some mergers are between roughly equal mass pairs. Others are highly asymmetric, with one black hole much more massive than the other. These mass measurements are, in themselves, scientifically significant. Before the era of gravitational wave astronomy, Our knowledge of stellar mass black holes came almost entirely from a small number of systems where a black hole was paired with a normal star, and the interaction between them produced observable X-ray emission. This gave us only a narrow, potentially unrepresentative sample. Gravitational wave observations have now given us a much richer view of the black hole mass distribution, revealing a population of objects heavier than many pre-LIGO theories predicted. But perhaps the most scientifically rich single event in the catalogue was not a black hole merger at all. It was the merger of two neutron stars. Neutron stars are what remain when a massive star, one typically between 8 and about 20 solar masses, exhausts its nuclear fuel and explodes in a supernova. The core collapses under its own gravity until it reaches densities far higher than anything achievable in a laboratory. Protons and electrons are forced together to form neutrons. The result is a sphere roughly 20 kilometers across, packed with the mass of 1 to 2 suns. A teaspoon of neutron star material would weigh about 1 billion tons. They are, in a sense, the densest stable objects in the universe that are not black holes. On August 17, 2017, LIGO and Virgo detected a gravitational wave signal from two neutron stars merging about 130 million light-years away. The event is designated GW17017, and its significance to science is difficult to overstate. The gravitational wave signal itself was different in character from the black hole mergers. Because neutron stars are less massive than many of the black holes observed, they spiral together more slowly, and the signal lasted for a longer time in the sensitive frequency band of the detectors, roughly 100 seconds, compared to a fraction of a second for the black hole mergers. And because neutron stars are made of matter, real physical matter, not the pure spacetime curvature of a black hole, their merger produced something the black hole events did not: light. Within approximately 2 seconds of the gravitational wave signal arriving at Earth, 2 space-based telescopes, the Fermi Gamma Ray Space Telescope and the European Integral Satellite, detected a burst of gamma rays from the same region of the sky. This was the first time a gravitational wave event had been directly associated with a source of electromagnetic radiation. What followed, over the next weeks, was an extraordinary campaign of coordinated observation. Telescopes on every continent and in space trained their instruments on the location of the merger, which had been localized by the combination of data from LIGO and Virgo to a patch of sky in the constellation Hydra. They found it, a new source of light, brightening over hours and then fading over days and weeks. This was what astronomers call a kilonova, the explosion produced by a neutron star merger. Kilonovae are remarkable. They are genuinely extraordinary events, even by the spectacular standards of astrophysics. The collision of two neutron stars creates conditions of extreme density, temperature, and neutron flux that do not exist anywhere else in the universe. In these conditions, atomic nuclei can very rapidly absorb neutrons, building up heavier and heavier elements that cannot be formed inside ordinary stars because the processes of stellar nuclear burning stop at iron and nickel. For decades, astronomers had theorized that most of the universe's supply of heavy elements, gold, platinum, silver, uranium, iodine, barium, strontium, and dozens of others, was created in environments exactly like this. GW17017 was the first direct confirmation. Observations of the kilonova's light showed the spectroscopic signatures of freshly created heavy elements, including strontium and almost certainly gold and platinum, being blasted out into space in the aftermath of the merger. Consider that for a moment: the gold in a wedding ring, the platinum in a piece of jewelry. Much of it was forged in an event like GW17087, in the collision of two neutron stars, billions of years ago in some distant corner of the universe. The material was scattered into space, eventually incorporated into clouds of gas and dust, and ultimately found its way into a new generation of stars and planets, including, eventually, the Earth and everything on it. GW17087 also inaugurated something that astronomers call multi-messenger astronomy, the simultaneous study of the same cosmic event through multiple independent channels of information. Before this event, astronomers had detected the same supernovae in both light and neutrinos, in the famous case of supernova 1987A, but GW17087 was the first event beyond our galaxy observed in both gravitational waves. From this single event, scientists were able to confirm that gravitational waves travel at the speed of light, to within about 1 part in a quadrillion, an extraordinary confirmation of general relativity. They obtained an independent measurement of the universe's expansion rate. They confirmed the long-theorized connection between neutron star mergers and the class of explosions known as short gamma-ray bursts, and they began to probe the equation of state of neutron star matter, the relationship between density and pressure in conditions that no earthly experiment can reproduce. Each gravitational wave event is a message, a signal dispatched from one of the universe's most extreme environments, encoded in the geometry of spacetime itself, and received by our detectors after a journey of millions or billions of light years. Reading those messages and understanding what they tell us is the central project of gravitational wave astronomy. One of the most striking things the messages have told us concerns the black holes themselves. Before the LIGO era, our knowledge of stellar mass black holes was largely confined to a small sample of objects in binary systems, where a black hole and a normal star orbit each other. These systems are detectable because matter from the normal star falls onto the black hole, heating up and emitting X-rays. But they represent only a narrow and possibly unrepresentative sample of the black hole population. Gravitational wave observations have revealed a much broader, and in some ways surprising distribution of black hole masses. Several of the black holes detected by LIGO and Virgo have masses between roughly 50 and 150 solar masses, a range that stellar evolution theory had suggested should be largely empty. Stars massive enough to directly produce black holes in this range are expected to be disrupted before they can collapse by a process called pair instability. High-energy photons in the star's core can spontaneously produce electron-positron pairs, reducing the radiation pressure that supports the star against gravity, and causing catastrophic collapse and explosion before a black hole can form. So where are these massive black holes coming from? One compelling possibility is that they are the products of previous mergers, black holes that were themselves formed when smaller black holes merged, and then went on to merge again. This kind of hierarchical assembly, in which black holes grow through a sequence of mergers, is predicted to occur in dense stellar environments like globular clusters, where black holes can find each other more easily. The existence of merging black holes in this mass range suggests that the universe has been busy assembling progressively larger black holes through repeated collisions, a history of violence written in the masses of the black holes we detect today. Gravitational wave observations are also contributing to one of the central unresolved debates in modern cosmology, the question of how fast the universe is expanding. This expansion rate, called the Hubble constant, is one of the most fundamental numbers in cosmology. It tells us the relationship between the distance to a galaxy and the speed at which that galaxy is moving away from us due to the expansion of space. But different methods of measuring it have for over a decade given systematically different answers, a discrepancy known as the Hubble tension. Some methods, based on observations of the very early universe, give a lower value. Other methods, based on observations of relatively nearby objects, give a higher value. The discrepancy is now significant enough that it seems unlikely to be a simple measurement error. It may be pointing toward new physics, something our current models of cosmology are missing. Gravitational wave observations offer an entirely independent approach to measuring the Hubble constant. When a gravitational wave source is detected and its host galaxy can be identified, as happened with GW17817, the gravitational wave signal itself tells you how far away the source is, while the galaxy's observed velocity tells you how fast it is moving away. Dividing one by the other gives you the Hubble constant. This method is free from the chains of calibrations and assumptions that complicate the other methods, and as the catalogue of gravitational wave events with identified host galaxies grows, the gravitational wave measurement of the Hubble constant will become increasingly precise, potentially resolving the tension or deepening it in ways that force a revision of the standard cosmological model. There is also the matter of the gravitational wave background, a pervasive, random hum of gravitational waves that permeates the entire universe, produced by the superposition of countless individual events too distant or too numerous to be resolved individually. Detecting and characterizing this background would tell us something profound about the history of the universe's most violent events. In 2023, a significant step toward detecting this background was announced. Several independent teams, using networks of millisecond pulsars, rapidly rotating neutron stars used as extraordinarily precise natural clocks, reported evidence of correlated variations in the timing of these pulsars, consistent with the presence of a gravitational wave background. The signal appears most likely to originate from a large population of supermassive black hole binaries, pairs of monster black holes, each millions to billions of times the mass of the Sun, slowly spiraling together in the centers of galaxies that have merged over the history of the universe. If this interpretation is correct, the background is a kind of census of the universe's most massive mergers, an integrated record of galaxy collisions and the slow inevitability of their central black holes finding each other. It is in a sense the universe's own ledger of violence, written in the language of spacetime. We are at the very beginning. The detections made so far, extraordinary as they are, represent a handful of signals pulled from what will eventually become a vast, rich and detailed map of the gravitational universe. The next generation of detectors will change the picture entirely. In Europe, a project called the Einstein telescope is being designed to be built underground, in a triangular configuration with arms 10 kilometers long. The underground location reduces the impact of seismic noise from the surface. The longer arms increase the detector's sensitivity. The triangular geometry allows it to determine the direction of incoming gravitational waves with much greater precision than the current L-shaped detectors. The Einstein telescope would be sensitive enough to detect binary black hole mergers virtually anywhere in the observable universe, and would hear the gravitational wave signals from neutron star mergers out to distances of many billions of light-years. In the United States, a complementary project called Cosmic Explorer envisions building 2 new L-shaped detectors with arms of 20 and 40 kilometers, up to 10 times longer than LIGO's current arms. At these scales, the detectors would be able to observe the full population of merging stellar mass black holes throughout the entire observable universe, mapping not just the black holes nearby, but tracing the history of black hole mergers across cosmic time. The most ambitious gravitational wave project ever conceived, however, is one that leaves the ground entirely. The Laser Interferometer Space Antenna, LISA, is a space-based gravitational wave detector consisting of 3 spacecraft flying in a triangular formation, with laser beams connecting them across separations of 2.5 million kilometers. That is roughly 6 times the distance from the Earth to the Moon. Operating in space eliminates all sources of ground-based seismic noise, and the enormous arm length makes the detector sensitive to gravitational waves at much lower frequencies than ground-based detectors can reach. These lower frequencies correspond to entirely different types of sources. LISA would detect the inspiral and merger of supermassive black holes, events in which black holes millions or billions of times the mass of our Sun spiral together and merge in collisions that are, in terms of total energy released, the most powerful events in the universe. It would observe thousands of compact binary systems within our own Milky Way. It would detect so-called extreme mass ratio inspirals, in which a stellar mass black hole spirals slowly into a supermassive black hole, tracing the geometry of spacetime around the monster with extraordinary precision. LISA was formally approved by the European Space Agency in 2024, with a planned launch in the 2030s. When it flies, it will open a frequency window on the universe that no previous instrument has ever accessed. And beyond LISA, physicists dream of something even more profound. The leading theory of the universe's earliest moments, cosmic inflation, predicts that a period of extraordinarily rapid exponential expansion occurred in the first fractions of a second after the Big Bang. This inflationary expansion should have produced gravitational waves whose wavelengths were subsequently stretched to enormous scales by billions of years of cosmic expansion. These primordial gravitational waves would carry information about the physics of inflation, about the energy scales and mechanisms of the universe's very first moments, encoded in their spectrum and polarization. Detecting primordial gravitational waves would be the closest humanity could ever come to directly observing the moment of creation. It would give us access to physics at energies 1 trillion times higher than any particle accelerator ever built. Whether the signal is strong enough to be detected by any foreseeable instrument remains uncertain. It depends on details of inflationary physics that we do not yet understand. But the aspiration is real, and the history of this field is a history of aspirations that seemed unreachable until they weren't. Let's allow ourselves a moment to gather everything we've traveled through together tonight, and let it settle into something quiet and whole. A little over a century ago, a man sitting at a desk with pen and paper worked out that space and time are not fixed and empty, that they are dynamic, that the universe has geometry that can bend and flex and ripple. He predicted, with mathematics alone, that the most violent events in the cosmos would send waves through that geometry, waves that would travel outward at the speed of light, carrying information about their origins, passing through everything in their path. For decades, physicists argued about whether those waves were real. For more decades after that, a long chain of extraordinary people, an eccentric experimenter in Maryland who failed but inspired, a careful analyst in Massachusetts who wrote the blueprint, a theorist in California who mapped the landscape, a Scotsman who knew how to make instruments sing, a manager who knew how to build a team, devoted their working lives to building something capable of detecting them. The instruments they built are, without exaggeration, the most sensitive measuring devices in human history. They can measure a change in distance 1,000 times smaller than the diameter of a proton, across arms 4 kilometers long, in the presence of all the noise and vibration and quantum uncertainty that the real world can throw at them. And on a quiet Monday morning, in September 2015, two black holes that had been orbiting each other since before our sun was born finally merged, releasing in a fraction of a second more energy than all the stars we can see produce as starlight in the same interval, and sent a ripple through space-time that crossed more than 1 billion light-years, stretched and squeezed the arms of 2 interferometers in Louisiana and Washington by 1,000th the diameter of a proton, and was recorded, analyzed, understood, and announced to the world. We heard it. After a century of theory and 50 years of building, we heard the universe speak. Since that moment, we have heard it speak many more times. We have heard the death knells of binary black holes that never produced a photon of light, whose existence was entirely invisible to every telescope ever built, and yet whose gravitational wave emissions carried their story to us precisely. We have heard two neutron stars collide and watched in the aftermath as the atoms of gold and platinum were forged in the fire of their collision. We have begun to detect the background hum of the universe's most massive mergers, a kind of deep gravitational music playing beneath everything else. And we are, still, just beginning. The Einstein telescope, Cosmic Explorer, LESSER, these are not fantasies. They are funded projects, approved missions, engineering challenges that are difficult but understood. When they come online, they will reveal a universe that the current instruments cannot see, the full history of black hole mergers across cosmic time, the internal structure of neutron stars under the most extreme conditions possible, the supermassive black hole mergers that mark the collisions of entire galaxies, and perhaps eventually, the faint signal of gravitational waves produced in the first fractions of a second after the Big Bang. Think about what it means to exist at this moment. Every civilization that has come before ours looked at the same night sky, collected the same light from the same stars, and went no further. We are the first generation in all of human history, the very first to perceive the universe through something other than electromagnetic radiation. We have developed a new sense. We have learned to hear the universe through the medium of space-time itself. The universe has been speaking since its beginning. Every black hole merger, every neutron-star collision, every pair of dense objects spiraling together across millions of years, all of it has been sending ripples through the fabric of reality, ripples that pass through everything and lose nothing. We simply had not, until now, developed the ability to listen. Somewhere out there right now, two black holes are drawing closer to each other. Their orbit is tightening slowly, over millions of years. The gravitational waves they produce are already traveling outward, in all directions. One day, perhaps long after anyone alive today is gone, the two black holes will spiral into each other in a fraction of a second of unimaginable violence, releasing a wave through space-time that will travel outward for hundreds of millions of years before reaching any instrument that might detect it. And somewhere on Earth, or in space, a detector will catch that wave. And someone, a scientist whose name we do not yet know, using an instrument we cannot yet fully imagine, will look at the data and see the story of two black holes written in the language of space-time. The universe is vast. It is old. It is full of things happening right now that we cannot yet see or hear or feel, but we are reaching for them. We are building the instruments and training the scientists, and asking the questions that will let us reach a little further with each generation. The ripples are out there carrying their ancient messages across the dark, and we are listening.